and welcome to today's edition again of Nonparametric statistics. So in the case of the parametric class of statistics, estimation of the unknown parameters is required to test the hypothesis. So this group of statistics often make unrealistic assumptions. What do we mean by unrealistic assumptions? We see in most of them talking about normality. Your data should be fairly normal. So if your data is not normally distributed and you have a very light data set, then you can invoke the central limit theorem, which allows us to make the assumption of normality and go ahead with our analysis. In non-parametric statistics, sometimes we call that distribution free test in some of the books. The focus is on the sign or the rank of the data rather than the exact numerical value of the variable. So what we do here is that you get the data and you arrange them in order, give them numbers serially according to the magnitude. Then after that, you take off the original data and now work with the ranked data as if they were the original data. So they do not specify the shape of the parent distribution. To say normal distribution, chi-square distribution, whatever it is, it doesn't follow any distribution. So that is one of the things that we need to take note of the non-parametric class of statistics. This non-parametric test can often be used in smaller samples, unlike the parametric test. So if the sample size is small and the data is not fairly normal, then we have problem with our results and conclusions. But then if we have non-parametric tests with smaller samples, it is okay to get correct results and make meaningful interpretations. So when measurement scale is not interval or ratio, we can still go ahead with the non-parametric statistics. Rejection of a hypothesis using non-parametric tests is essentially convincing because non-parametric tests generally make fewer assumptions about the population. So you can imagine we saying that the data should be normally distributed, but then we look at it and it's not normally distributed. What are we supposed to do? If we are going to reject the known hypothesis or not rejecting it, we will have problems because the assumption is not met. It's more like saying, let's go and buy a machine, and they've written there on the machine 1 year warranty, and the warranty, you're not supposed to do anything to it, not supposed to put any information, you're not supposed to put anything on top of it, don't let it drop, something like that. So if you let it drop, then that assumption is broken. You cannot return it again. So it's the same thing with data sets. Once we say it should be normally distributed and it's not, then that rule is broken. You cannot make the conclusions that you would have made if the data was normally distributed. If two methods are justified and have similar power, then the principle of Occam's razor favors the simpler method. So yes, so you can imagine if I have so many variables and so many conditions, if all of them are justified, definitely I would go for the one with the fewer variables and the one with fewer principles, because I don't want to stress myself so much. All of them will give me the same result, and one of them is going to task me so much than the other. So definitely I'll go for the simpler one. So for this reason, statisticians are often attracted to non-parametric statistics, and mostly, particularly in applications where data are likely to be ill-behaved and when samples are small. Ill-behaved here is, we mean when the conditions are not favorable to the statistical test that we want to use. The most popular non-parametric tests are based on a simple idea. Sort the values from low to high and analyze only their ranks, ignoring the actual values. So after arranging them in order, let's say for example, you have this data. So definitely this won't be, let me add another one called 10 and 300. So this is a data set. If we want to use this data set as it is, we are going to have problem. For example, calculate the mean of this one. Because of this 300, the mean is going to be high. So we tend to use non-parametric statistics when we have things like this. It's not normally distributed, we have outliers, or we have ensure the data is ill-behaved. So in this case, all you have to do is rearrange this one and give them numbers. So I would have given this 1, 2, and this is the same as that 2. So I would put 3 here first. Then we move to the next one, 4, 5, 6, and 7. Now where we have the ties, I will have to add those rungs. The 3 plus 2 divided by 2 because they are only 2, and that would have given me 2.5. So I would give this one here 2.5, and I'm going to give this one 2.5. So I would just ignore this original data set and now work with the ranked data. And that is what non-parametric statistics do. That is just what I'm trying to explain. So why rank-based non-parametric tests? They are versatile and flexible in application and simple in calculation. So if you as we are going to do the calculations, you will soon see that they are much simpler when you are using them for calculation. You can imagine the normal distribution. The formula is so huge, so it is difficult most times to memorize that, or even to, if you know the formula, it takes you time to understand how to go through the calculations. Again, they enable simple hypothesis testing on data of the various design types and have a good approximate properties for live samples. So again, if we are looking at normality or the central limit theory, this one too, we can do approximations if we have a larger sample size, and the properties are very good as compared to the parametric cases. When distributions are not normal, these tests have greater statistical efficacy than their parametric counterparts. So yes, the distributions of the parametric tests, they all follow these assumptions, and normality is one of the assumptions that cuts across most of the parametric tests. So once the data is not normal, then we have a greater result when we use the parametric tests instead of non-parametric tests instead of the parametric statistics. So use non-parametric methods only when the original data are ranked or are quantitative but do not appear to originate from normally distributed populations with equal variances. So even though with the non-parametric statistics it's easy to calculate, it gives us much efficacy when the data is ill-behaved, we still have to be cautious in using it, because overusing this can cost you more than using the parametric statistics. So it is not all the time that you see non-parametric statistics and use them, unless it is very necessary to use them. All the conditions are not met and you have no way of remedying the situation. So you can now use your non-parametric statistics in place of your parametric statistics. Do not adopt one of these tests described in this series of lectures merely as a matter of computational convenience. So as we are going to go through them, you will see some of them are so very good that you would waste, okay, let me use this one because it's simpler to calculate. So why do I have to go through a rigorous one when this one, it is very much simple. So let's be careful when we are using them, unless you are very convinced that that is the only option. Now the reason is that they are less likely to detect a false null hypothesis than the corresponding t-test or the f-test would do. For other statistics, it plays a crucial role in many non-parametric statistics testing methods, and that is because we are using the ranks, and non-parametric other statistics actually arrange the numbers in orders and uses the ranks. Okay, as we will see shortly, they do not depend on the population distribution and easy to use. However, if you go deep into other statistics, you realize that it's becoming a little more difficult than you would think initially. So let's define what other statistics is. Let x1, x2, x3 up to xn be a random sample drawn from a population x, and xi, where I is equals to 1, 2, 3 up to n, be independent and identically distributed. We sort the observed values of xi from low to high, as we can see here. So this one here is different from the first that you've seen. So x1, x2 are the original values, and here we are simply rearranging the original values according to their magnitude from low to high. Then this group of data here is what we call the order statistics of the sample x1 to xn. So x1, as you see, is different, is not the same as x bracket 1. So this indicates the order, and this indicates the original values from the data set. Now xi is the ith order statistic if you rearrange them. So for example, I have my data set x is equals to 8, 3, 4, and 10. This is what I have. So if I'm going to arrange it, I would rearrange it as 3, 4, 8, and 10. So in the first one, my x1 is equals to 8, x2 is equals to 3. But then if I come to the rearranged variables or rearranged data, my x bracket 1 is equals to 3, x bracket 2 is equals to 4. So it's simply looking at the position after you have rearranged them in order. So any x1 is a function of a sample x1 to xn and are therefore considered random variables, but not mutually independent. Why? Because if I remove 4 from here, then my x2 will not be 4 again, it will become 8. So the position of 8 will depend on the presence of 4 in the data set. So they are not mutually independent. Why order statistics? They have a good statistical properties such as sufficiency, and so that is the reason why we want to study that, or we use that to apply in our non-parametric case. They can be used to study the properties of percentiles for large sample sizes, and again percentiles and the estimation of percentile functions or population distributions are the basic content of non-parametric estimation. So if we study order statistics, then it becomes a little easier for us to look at non-parametric estimations. Let's take the median for example. The median rearranges the data set from low to high and picks the number in the middle. So we are simply dividing the area of the population distribution into two parts. The probability that any observation is to the right or left side of the rearranged data is simply half, 0.5. So the median is not sensitive to a difference in the shape of the population distribution, but is sensitive to a difference in the central location. So if the central location shifts, then that changes the value of the median, but then the shape can shift from anyhow, but you still have your central point. So owing to this property, the median plays an important role in rank-based non-parametric statistics, such as those we are going to consider in this series of lectures. So let's look at a common diagram. So this was adopted in a textbook that I'm using, which is 2016. They give us a very nice diagram indicating the different non-parametric statistics and their parametric counterparts. So if we have one sample case, then the non-parametric statistics that you can actually perform on this, or test that you can perform with the one sample data, it's Rand's test for randomness and Wilcoxon sign rank test. Now their counterpart, Wilcoxon sign rank test counterpart, is the one sample t-test, as we saw in the t-test analysis. If you have two samples, then we can do two things. One is independent samples, or one is paired samples. Independent samples because first sample is not the same as your second sample. The observations are different. In the paired samples, it's the same observation, that you are taking measurements 2 times. That is when you have before and after situations. But then the independent samples could be, let's say, patients in one hospital and patients in another hospital. You want to find something between them. The paired one we are simply looking at, let me say, interventions. Okay, you have one observation, but you want to measure an intervention using that observation. So you take a measurement before the intervention and after the intervention. That is a paired sample. So in the case of the independent samples, we use the Mann-Whitney test. That is this. And then in the case of the paired samples, we can use two things. One, the Wilcoxon-Run test, like we did here, or we can use the Spearman-Run correlation for that purpose. Now, if the data follows normality, is normally distributed, and the conditions for a parametric test is satisfied, then we can use the two-sample t-test in place of the Mann-Whitney test. And we can use the paired t-test in place of the Wilcoxon-Run test or the Pearson correlation to replace the Spearman-Run test. So this is where you have the two samples situation. What if we have more than two samples? Yes, you can still do a t-test, but a t-test will inflate something, your type 1 error, the alpha value, or if you like, the significance level. So it is not advisable to use a t-test to do multiple comparisons when you have more than two samples. However, we have a one-way ANOVA that can do the work of a t-test when you have more than two categories to compare. Now, in non-parametric statistics, if you have this case, the one-factor situation is where you have, for example, you have fertilizer types. So fertilizer is a factor, and the different types of fertilizer you have to apply at the different levels. So that is a one factor with different levels. So we can use the Kruskal-Wallis in place of the regular ANOVA if we don't have a good data set that is normally distributed or have good parametric properties. Now, if you have two factors, let's say you have the fertilizer case, but then soil type is a problem. You want to also look at the soil type. So you have one factor as fertilizer and you have another factor as soil type. So you can use the Friedman test in place of the randomized block ANOVA when you have situations like that. So this is a summary of the non-parametric statistics that you can do depending on the kind of data that you have.